Assalamu alaikum. This video will be part 2 of the tutorial 2 inshallah. It will be about compressors. Let's start with the first question. Air. So we have air and we will treat it as an ideal gas. Is compressed. Compressed means we have a compressor that compresses the air steadily. And compressor is already a steady device by an 8 kilowatt compressor. 8 kilowatt means, okay, kilowatt is power, kilojoule per second, it is in rate. 8 kilowatt watt means it is an input power. Why input, not output power? Because it's a compressor is a work consuming device, so it will provide a work in, so it can compress the air from this pressure to this pressure, so it increases the pressure of the air and also produce consume work. This is a consuming work, so this one is a work dot in, not out. For the previous video about turbines, it was out. Here for compressor, always the work is in. Okay, from 100 kilopascal, so this one is P1. Okay, and T1 is equal to 70 degrees Celsius, which is equal to 90 Kelvin. Okay, to a 600 kilopascal, this one is P2, and a 167 degrees Celsius, that is T2. Okay, which is equal to, this one is in Kelvin, we have to add 273. Okay, it is 440 Kelvin. Okay, get 273. What else? We have at a rate of 2.1 kilogram per minute. So he gave me the mass flow rate because it is per time. 2.1 kilogram per minute. I will multiply this number by 1 minute over 60 seconds. So I can get 0.035 in kilogram per second because we usually deal with seconds. Okay, neglecting the change in kinetic and potential energies as usual. Determine the increase. Increase means change. Okay, so state 2 will have a higher exergy than state 1. So he wants for me to find delta X. Okay, delta X, should it be in rate form or just delta X? You want for me to find psi 2 minus f psi 1 times the molar mass, or only f psi 2 minus f psi 1? Actually it doesn't matter. At the end you have the mass flow rate, multiply with the mass, you will get any one of them. Okay, it doesn't matter. So in the question, in the exam, usually the doctor give you the unit that he wants you to find the requirement. Okay, you want if he wants in per unit mass, if you want it in a rate form, he will tell you in the question. Okay, in this question we will find it in per unit mass. Okay, so we will find psi 2 or flow exergy in state 2 minus in state 1. This one from the long equation we can find it, H2 minus H1 minus T naught S2 minus S1. Okay, for the second part or part B, the rate of exergy. Now he said rate. The previous one he didn't say rate. Okay, maybe you can guess that is the reason we will find it in per unit mass, but it doesn't matter. It's not a big deal. Just multiply by mass flow rate, and in the exam it will be clear inshallah. Okay, the rate of exergy destroyed during this process, so he wants to find X destroyed. Okay, and X destroyed, we usually find it in two ways. Either we say X destroyed, and here it is a rate is equal to the irreversibility in rate this time, and it is equal work reversible useful in and why in not out, because now we are talking about compressor and we have work in, okay, minus work reversible dot in, or we use this equation T naught is generation, and in this time we want the rate, so it is S dot. Okay, which one shall I use? If I use both of them, they will give me the same number. So which one shall I use? Actually, you cannot use this one, but you can use this one. Why? Because let's see, of course the problem will be in S generation, the rate of X entropy generation. T naught is okay, it doesn't matter. Okay, for S generation we get it from the entropy balance. S in dot minus S out dot plus S generation dot equal to delta S rate of entropy change in the system. We know it is a steady device, so this term is equal to 0. Okay, and for entropy transfer, we don't have entropy transfer by work, so you only have either with heat transfer or with mass transfer. With mass it will be m dot s small. Okay, with heat transfer it will be q dot over t. Okay, the problem is when of course we have mass flow rate, we have inlet and outlet, so we can say it is, we have m dot s1, okay, it is the inlet, minus m dot s2, the outlet. Okay, but what about the heat? The heat, he didn't mention anything about that compressor is adiabatic, so there may be heat transfer happened in this system or in this compressor, but he didn't mention. It doesn't mean that if he didn't mention heat in the question, this will mean it is adiabatic. No, if he wants you to know it is adiabatic, he will say it is an adiabatic. Okay, so maybe it will be, there be a heat transfer, and you should include it in here, so you have to include it in this system. Okay, you have to add for out q dot out over t, but you don't have q. That is the problem. So that is the reason why I cannot find the Exergy destroyed using this way. Okay, if he said adiabatic in the question, then this one will not exist, and you will use only this one, and okay, it's fine, you can use this equation. We will see in the next question, inshallah. Here we have the work useful in dot minus the work reversible in dot. Okay, work reversible useful in dot this one is the actual one, means the 8 kilowatt, but the work dot reversible in, we have to find it from where? From the Exergy balance as usual. Okay, so you have also to find, if you want to use the X destroyed, or you want to find it, we have this one, it is 8 kilowatts. I want to find the work reversible, I have to use the Exergy balance. So the Exergy balance in rate form, X dot in minus X dot out minus X destroyed equal to delta X dot in system. Okay, it is a steady process. Okay, any delta in Exergy balance, entropy balance, energy balance, this one is 0 in the steady devices because steady. Okay, no change in time. It is a reversible process. There is no Exergy destruction. If I want to find the reversible work, I have to assume it is a reversible process and there is no Exergy destruction. Okay, so this one is 0. I have Exergy transfer by mass, so I will say it is m dot psi 1 flow Exergy 1, because n means 1, okay, out means 2. It is n, right? It is a work reversible n, so I have to add also work reversible n. Okay, for out I will have the Exergy transfer by mass. Okay, this one m dot psi 2 or flow Exergy 2, And for heat, exergy transfer by heat, this one is 1 minus T over T times Q, this exergy by heat. I have to assume it is adiabatic compressor. يعني it may be confusing here. You said it is not adiabatic, and there is no it might have this equation. It might have a Q out, okay, because he didn't say it is adiabatic. But here you say you have to assume it is adiabatic. Why? Because this one I want to find the work reversible. The purpose of this equation or my assumption is a work reversible. What is the meaning of work reversible? يعني what is the definition of work reversible? Work reversible means the maximum in the work producing devices and the minimum in the work producing consuming devices. Okay. Reversible work is the maximum amount of useful work that can be produced or the minimum work that needs to be supplied as the system undergoes process between two specified initial and final state. Okay, this useful work output or input obtained or expanded when the process between the initial and final state is executed in a totally reversible manner. No irreversibility, no entropy. A totally reversible. Totally reversible means there is no irreversibility. Means يعني you take the system and its surrounding. Okay, the system and its surrounding, as there is no the return to the initial state. Okay, there is no heat transfer. If there is heat transfer, means there is irreversibility. The meaning of irreversibility means that there was a heat transfer out or in. Okay, this heat transfer will change the environment temperature, or will be a heat going to the surrounding. Okay. How heat transfer? Heat transfer from a high temperature, تمام, to a low temperature, from T2 to T1. So there will be a temperature difference. Temperature difference is a source of irreversibility. So meaning that there is a Q out, okay, means that there is a temperature difference or change in there is a temperature difference delta T, means there is irreversibility. And the definition of reversible work is a totally reversible. Meaning of totally reversible means that is the environment and the system will return back to their initial states. So if you have heat, the heat is gotten. Okay, you produce heat. How you can return this heat again to the previous or initial state? You will supply Qn from where? You have to assume there is no heat. Okay, there is no the system will be an adiabatic system if you want to solve for the reversible work. Okay, that's why I will not include heat here. Okay, but this question is not adiabatic, that's why I didn't use this equation. Okay, so this one will be equal to 0. Work result dot reversible n will be equal at the end m dot exergy flow 2 minus exergy flow 1. Okay, and then after I find this one, I will subtract it from 8. I will get x dot destroyed. But first we want to find delta x in per unit mass, per kilojoule per kilogram. For H2 minus H1, I have to assume either constant specific heat or variable specific heat. Okay. For this question, I will assume it is a variable specific heat. Okay, I will say this assumption, it is a variable specific heat. Okay. So I have that at state 1, I have a state 1 the temperature, and I have the state 2 the temperature. So it is easy for me to use table A17. So that is why it is easier to use a variable specific heat. Okay, and directly if you have only one property, you will find it from the table. Okay, so let's write this one, because if I know psi2 minus psi1 or the change in exergy per unit mass, I will find it here. I already have the mass flow rate. I will find the work reversible n. Okay, so let's write the states or find it from table A17. Okay, I have at state 1 T1 equal to 290 Kelvin. Table A17 is in Kelvin, so you have to use the Kelvin. Okay, I want to find H1, and for S, how can I find S? يعني H1 is there in the table A17. Where is the thermodynamics tables? Table A17. For air, I have H, but I don't have entropy. I have S naught. Okay. How to find the entropy itself? يعني S2 and S1. We have equation when it is a variable specific heat. Okay, variable specific heat. We'll use this equation if variable specific heat assumption with table A17. So I have to find from table A17 S2 naught and S1 naught are from the table A1 or A2A, and the pressure I already have the pressures. Okay. So for S2 minus S1, for S2 minus S1, I have to use this equation. This equation is S naught, S2 naught minus S1 naught minus R ln B2 over B1. Okay. For R, from table A1 or table A2A, let's find it later because we want to use table A17. Returning back to T1, 290 Kelvin, I want to find H1 and I also want to find S1 naught. Okay. For H1 290, this one H1 is 290.16 and S naught is 1.66802. Okay, so let's write them. 290 0.16 kilojoule per kilogram, and S1 naught is 1.66802 kilojoule per kilogram Kelvin. Okay, for T2 it is 440 Kelvin, and I want to find H2 and S2 naught. Okay, 440. This one H is 441.61 and S naught is 2.08870. Okay, H2 is 441.61 kilojoule per kilogram, and S2 naught is 2.0887 kilojoule per kilogram Kelvin. For R, I will go to table A1 or A2A. I have air, so R 0.287. Okay, or from here for air R 0.287. Okay, it's 0.287. The unit of specific entropy, kilojoule per kilogram Kelvin. Okay, then now I can find S2 minus S1. Okay, so S2 minus S1 is equal to S2 naught 2.0887 minus S1 naught 1.66802 minus R 0.287. Okay, ln B2 over B1. B2 over B1 is 600 over 100. Okay, S2 minus S1 is equal to negative 0.09356 kilojoule per kilogram Kelvin. Okay, for I got H and H1 H1, so let's go here to find the exergy change per unit mass. So phi 2 minus phi 1 will equal to H2 441.61 minus H1 290.16 minus T naught 290 given the question, and S2 minus S1 is negative 0.09356. This will give me 178.6 kilojoule per kilogram. So that is for part A. For part 2, we want the work reversible in. we said it is equal to m dot phi 2 minus phi 1, psi 2 minus psi 1, phi this in closed system. Okay, the mass flow rate is 0.035 kilogram per second. This one is 178.6. The result will be 6.25 kilowatt. Okay, so X destroyed equal to reversibility equal to W dot U, or actually يعني actual work in the compressor consumed by the compressor minus the work reversible in dot, and this will equal 8, this given in the question, and this one is 6.25, will give me 1.75 kilowatt. This one is the Exergy destroyed, the rate of Exergy destruction or Exergy destroyed. Okay, let's move to the next question. Next question is 857. I have argon gas, and we will treat it as an ideal gas. يعني بص يعني دايما gases we treat them as an ideal gases. With an adiabatic, this time we have an adiabatic. Adiabatic means no heat transfer. No heat transfer. No Q in or out. Transfer. Okay. We have a compressor, so let's draw the compressor. Okay, we have inlet and we have the outlet. We have the power consumed by the compressor. Okay. At the inlet enters at 120 kilopascal, so B1 is 120 kilopascal. T1 is 30 degrees Celsius or 303 Kelvin. With a velocity, so V1 is equal to 20 meters per second, and exits at pressure P2 equal to 1.2 megapascal, and T2 is 530 degrees Celsius, and this one is equal to 803 Kelvin. Okay, at V2 80 meters per second. Okay, the inlet area of the compressor, so A inlet, which is A1 plus inlet 1, is 130 centimeter squared. If I want it to be in meter, I have to multiply by 10 to power negative 4. So from centimeter to meter, 10 to power negative 2, power 2, so it is 10 to power negative 4. It will give me A1 equal to 0.013 meter squared. Okay. Assuming the surrounding to be, so T naught is 25 degrees Celsius. Determine the reversible power input and Exergy destroyed. So he wants from me to find the power input from the compressor work reversible, but the reversible one يعني reversible N, it is power, so it is dot. Okay, this is part A, and for part B he wants the Exergy destroyed. Okay, خلاص the question is in rate form, and I have the area. If you are given the area, predict that you will have the mass flow rate in the system. Okay, we will see why. Okay, so this one he wants the rate of Exergy destroyed. Okay, why I am saying if you have areas, then you will use the mass flow rate, because usually in closed system we say that the volume, the mass is volume over the specific volume. Here we don't have mass, we have the specific volume, the mass flow rate. So it is volume flow rate over the specific volume. The volume flow rate is have an equation equal to the area times the velocity. That is why I'm saying it is if you see area, so you will need to find the mass flow rate over the specific volume. That is a velocity, not the volume. Okay, this one velocity. Okay, so I have the area of the inlet, so I need to use with it the velocity of the inlet and specific volume at the inlet state. Okay. That's it. Okay. How can I find the specific volume? I don't have steam or refrigerant, so I can use the tables. It is an ideal gas, so I have to use the ideal gas equations. Okay, so V is equal to RT over B, and that is V1. Okay, so T1 B1. I have T1 B1. R for the argon. For the argon, you can find it from table A2A or A1 0.2081, or from here argon 0.2081. Okay, so R is 0.2081 kilojoule per kilogram Kelvin. Okay, that is for the mass flow rate. Okay, let's return back to the work reversible N. We usually said work reversible N, we use what? We use the Exergy Balance. Okay, X dot N dot. Okay, X dot N, X dot out, minus X destroyed, and it will be 0. X dot system, and change in X dot system, and it will be 0 also, because it's a steady device. So this one will be 0 because it is steady. Okay, and this one is 0 because we assume it is a reversible process, because we want to find the reversible work, or the reversible bar. We assume it is an adiabatic, so there is no heat transfer by there is no he gave me already it is adiabatic, even if I didn't assume this adiabatic, so there is no exergy transfer by heat. X dot N is what? Is M dot exergy flow 1. I have also work N is a compressor, so dot N, reversible N, that the one that I want to calculate, minus the exergy flow times the mass flow rate out. Of course, the mass is the same. It is the inlet equal to the outlet. If you make a mass balance, M dot N equal to M dot out equal to M dot in general. Okay. This one is equal to 0. So the work reversible N, the usual equation that you will find at the end, is equal to M dot, in brackets, psi 2 minus psi 1. Okay. M dot here, M dot. Okay. This one will equal to M dot psi 2 minus psi 1 is H2 minus H1 minus T naught S2 minus S1. I have velocity, right? He gave me the velocity, so I have a change in kinetic energy, V2 squared minus V1 squared over 2, and don't forget, when we substitute in this equation, you divide by 1000. Okay, we don't have change in potential energy, there is no elevation. If you are given an elevation Z1 and Z2, the question, but I don't think you will be given any question about potential energy. But if you are given a question about potential energy, you have to put the potential energy is G Z2 minus Z1. Okay. I have the mass. Yes, I can find the mass from here. Let's find the mass flow rate. So first I need to find, I have the velocity and I have the area. I need to find the specific volume. So the specific volume V1 equal to RT1 over B1, and equal to R 0.2081. T1 is 300 in Kelvin. Okay, you have to put it in Kelvin because already they are in Kelvin and you want to find everything in Kelvin. Okay, B1 is 120 kilopascal. Bardo, here is kilojoule. Okay, so you have to put kilopascal. Okay, equal to 0.5255 meter cubed per kilogram. Okay, then the mass flow rate will equal to A1 V1 over the specific volume 1. This one is the velocity, not the volume. Okay, A1 is given in meter squared is 0.013 meter square times 20 meter per second over V1 0.5255 meter cube per kilogram. This will give you 0.495 kilogram per second. So that is the mass flow rate for H2 and H1. Here I have to make an assumption it is a constant specific heat. Okay, if you made an assumption it is a variable specific heat, you will not find anything about argon in table A17. So يعني in table A17 you will not find for argon. يعني here it is air, nitrogen, oxygen, hydrogen. So you will not find carbon dioxide. You will not find for argon. So you have no other choice than assuming it is a constant specific heat. So you will say it is a constant specific heat. Okay. And then H2 minus H1 with constant specific heat we use CPK, but in variable specific heat you cannot use any equation that contain CB or CV or K. Okay, H2 minus H1 is equal to CB T2 minus T1, and CB should be the average CB. يعني you have to find it as the T average, T2 plus T1 over 2. But if you go to a table A to B, where there is variable temperatures like this one at various temperatures, you will not find the argon, but you will find only these 6 gases. So if you have these six gases, you have to find the average temperature and then find CB or CV at these average temperatures. Okay, but here for argon you don't have other choice. You don't have this a table for a various temperature for argon, so you will assume this CB, the given one in the table A2, this one that we will use. Okay, for argon you will use this one, 0.5203. okay, from table A to A. So here I cannot use this equation. خلاص, I don't have a table. So 0.5203, that is CB. T2 and T1 is given in the question. 530 minus 30 degree Celsius, I think. Yes, okay. This will give you H2 minus H1 is equal to 260.15 kilojoule per kilogram. For S2 minus S1, you see that it's a constant specific heat, so I have to use the usual equation for constant specific heat. S2 minus S1 equal to CB ln T2 over T1 minus R from table A1 or table A2A ln to B2 over B1. Okay. So S2 minus S1 CB already know 0.5203 ln T2 and T1 should be in Kelvin, so 803 over 303 minus R from the table 0.2081. Okay, or from here also 0.2081. Okay, 0.2081 ln B2 over B1. Okay, S2 minus S1 is equal to 0.02793 kilojoule per kilogram Kelvin. Okay, I want to find the work reversible N. Okay, so I will use this equation. So M dot is 0.495. H2 minus H1, we got it 260.15 minus 298, that's T naught. For S2 minus S1 is 0.02793 plus V2 is 80 squared minus, you have to put the bracket, in the calculator put the bracket, you have to put the bracket because there is negative here, the only square of about the 20 only the 20 itself يعني over 2, and don't forget to divide by 1000 because that is in meter squared or second squared. You have to put it in kilojoule per kilogram because all of these things are in kilojoule per kilogram for these terms. Okay, and close the bigger bracket. The work reversible N will be 126 kilowatt. The second part, we want to use what is the second part? X destroyed. Okay, we didn't talk about X destroyed. Okay, let's talk about the Exergy destroyed. Exergy destroyed, we said we have two ways, and in the previous question we didn't use the T naught over S gene, okay, because it wasn't an adiabatic system. Okay, so in this question I can use this equation because it is adiabatic. He said in the question it is adiabatic system. Okay, and also I can use the other equation, but did he give me the work useful, the actual useful work? No, he didn't give me. So in this case you have to only use the T naught S gene. Okay, so we'll use this one this time. In the previous question we used the other one. Okay, so X destroyed is equal to T naught S dot generation, and equal to for S generation you have to use the entropy balance Sn dot minus S dot out. Okay, plus S dot generation equal to delta S system, which is equal to it will be 0 because it's steady. For Sn and S out I have يعني mass or entropy transfer by mass, so it is m dot S1 minus m dot S2. I don't have heat transfer because it is adiabatic system. There is no work, there is not entropy transfer by work. Okay, يعني always work entropy transfer by work is 0. Okay, I wrote it in the summary. S dot gen equal to 0, so S dot generation is equal to m dot S2 minus S1. Okay, I have m dot S2 minus 1. I already got it. So let's find X destroyed. It will be T naught m dot S2 minus S1. T naught should be in Kelvin, so it is 298 times 0.495. The S2 minus 1 is 0.02793, and this will give you 4.12 kilowatt. Okay, and this for this question. So let's go for the third question. The question is 860. Now we have carbon dioxide, CO2. It is we are assuming, or we will treat it as an ideal gas. Okay. Enters a compressor, so we have a compressor. We have an inlet at 100 kilopascal, so we have an inlet B1 equal to 100 kilopascal at temperature T1 300 Kelvin. At a rate, give me the mass flow rate 0.2 kilogram per second, and exits at, so this one is P2 600 kilopascal and T2 450 Kelvin. Okay, determine the power input. So I have a power input, also will be a power input. Determine the power input of the compressor to the compressor if the process involves no irreversibility. So he wants for me to find delta W dot reversible N. Okay, the surrounding to be T naught equal to 25 degrees Celsius, which is equal to 198 Kelvin. Okay, so let's find the work reversible in. We know it is as usual from the Exergy balance. So x dot in minus x dot out minus x dot destroyed equal to delta x dot system. This one is 0 because it is a steady device. Okay, and this one is also 0 because it is a reversible process. Okay, and for the reversible process is the minimum or the maximum, so there is no heat transfer, so I will assume there is no exergy transfer by heat, so I will have only exergy transfer by mass, which is m dot psi 1, and I have the work reversible in that I want to find. Okay, for the outlet I will have only the exergy transfer by mass. Okay, equal to 0. So work dot reversible in, the usual equation that we get at the end, m dot psi 2 minus psi 1, or exergy flow, whatever. Okay, this one will be equal at the end m dot h2 minus h1. Let's make it like this, h2 minus h1 minus t naught. He didn't mention anything about velocities or elevation, so I will neglect the kinetic velocity, change in kinetic energy and change in potential energy. So it is only this these two terms. Okay, I will assume it is a constant specific heat. Okay, constant specific heat. This is an assumption, you are free to choose. Constant specific heat. Okay, H2 minus H1 will equal to CB average T2 minus T1. For carbon dioxide, I have a table for the various temperatures, so I have to get the CB at T average T2 plus T1 over 2. And this will equal to 450 plus 300 over 2, and this will give you 375 Kelvin. So CB average at 375 Kelvin, so let's find it here. Carbon dioxide, this one, 375 is exactly at the middle between 350 and 400. So I can take the value at 350 and 400 and add them and divide them by 2. Okay, so let's do this. CB average will equal 0.895 plus 0.939 over 2. 0.895, this one at 350, and 0.939 is the one at 400, this one. Okay, I will add them and divide it by 2, so I can get my CB at the 375. It is a faster interpolation. 0.917 kilojoule per kilogram Kelvin. Okay, so H2 minus H1 CB average equal to 0.917. T2 minus T1 is 450 minus 300, and this will give you at the end 137.55 kilojoule per kilogram. And for S2 minus S1, it is a constant specific heat, so we'll use the equation related to constant specific heat. It's S2 minus S1 CB ln T2 over T1 minus R from table A1 or T2A, table A2A, R ln B2 over B1. Okay, CB, the average one, this one, 0.917. Okay, ln T2 450 over 300. For carbon dioxide, R is equal to carbon dioxide 0.1889, or from here also carbon dioxide 0.1889. Okay, minus 0.1889 ln B2 600 over B1 100. Okay, so S2 minus S1 at the end will equal to 0.0335 kilojoule per kilogram Kelvin. Okay, so let's find the work reversible. So m dot, it is given the question 0.2. H2 is what? H2 minus H1, we have the value 137.55, and my T naught given in the question 298 Kelvin, and the entropy change is 0.0335. This will give me the work reversible dot n is 25.5 kilowatt. And that is for this question. For the last question in this video, inshallah, let's put it here. 862. Now we have a refrigerant, so we are predicting to use the tables of the refrigerant from table A11 to table A13. Okay, enters an adiabatic. So adiabatic, خلاص adiabatic يعني no heat transfer. No heat transfer. Okay, compressor at negative 30. So this is T1. And this is equal to 243 Kelvin. As the saturated vapor, so the quality is 1, and I will get any value at at saturated vapor, so I will use G يعني gas for gas at a rate of 0.45 meter cubed. Meter cubed is a volume يعني volume meter cubed per minute, so it is a volume flow rate. Now he gives me a volume flow rate. It is equal to 0.45 meter cubed per minute. If I want to make it in per second, or multiply by 1 minute or 60 seconds, this will give me 7.5 times 10 to the power negative 3 kilogram. Not kilogram. يعني this one is meter cubed. This volume flow rate per second. Okay, that's different. Okay, and if I have volume flow rate, already I can get the mass flow rate. If I have the volume flow rate, I will divide by specific volume, and I will get the mass flow rate. Okay. This volume flow rate at the inlet, so it is V1, V.1. So I have to find the specific volume at state 1. Okay. He said also it leaves at 900 kilopascal. So B2 900 kilopascal. T2 is 55 degrees Celsius, and in Kelvin 328 Kelvin. Okay. He wants from me to find and determine the power input of the compressor. He didn't say without irreversibility, the reversible power, only power. So he wants for me to find only the actual power. He didn't mention anything about reversible. Not usually, usually okay, we solve for reversible, but if he didn't mention anything, first it is the actual one. Okay, work. Okay, it is dot because it is power, but it's not reversible. It is N because it is compressor, even if he didn't say input. Okay, and B, the isentropic efficiency. Isentropic efficiency, it is not the second law efficiency. Isentropic efficiency is eta C for the compressor. Okay, and for part C, the rate, so it is in per second. So dot of exergy destruction, yani x dot destroyed or destruction is the same. And the second law efficiency, let's say it is D يعني. Okay, part D. Second law efficiency, second law يعني 2I, second law efficiency for the compressor. Okay. Take T naught. is equal to 27 degrees Celsius, and in Kelvin is 300 Kelvin. Okay, so let's find the power dot n. Okay, يعني if you are talking about actual يعني without talking about reversible work, without exergy, without anything, so we are talking about thermodynamics. In thermodynamics, in chapter 5 in turbine, compressor, steady devices, we usually used the energy balance. Okay, so you have to use the energy balance. So E dot n equal to E dot out. I will not write delta E system and we'll put it 0 because it is steady. خلاص, the steady devices E dot n equal to E dot out directly. Okay, what you have in the inlet is m dot times the enthalpy. Okay, m dot h1, because the enthalpy يعني contain with the mass flow rate the energy produced by the يعني the internal يعني the energy of the internal energy moved by the flow work. Okay, يعني because h1 is u1 plus rho b1 v1. Okay, that is why I am putting energy in n dot m dot h1. Okay, also I have work power, the one that I want to find. Okay, so it is the work dot n. Let's say this one is the actual, so let's call it the actual one. Okay, and I have at the exit m dot h2 actual بقى يعني ايه, it is actual. Why I'm not saying h1 actual, I'm saying only h2 actual. We will see in a moment why I'm saying this. Okay, then I have to find the work in dot actual. يعني let's say assume it is not, I will not say the h2 actual and not h1 actual. Let's say leave it like this until now, and then we will know. Okay, m dot h2 minus h1. Okay, that is the work dot n actual will equal from the energy balance this equation. Okay, for the isentropic efficiency, when he says isentropic efficiency, when you see isentropic efficiency in the questions, in the statement of the question, or in the requirement of the questions, so this means that this question is about an actual device. Okay, and you cannot solve an actual device without solving the ideal one first. Okay, يعني this will be the usual that you will find if you face any actual cycle in the next chapters, inshallah. You have to find the ideal one, then find the actual one. Why? Because the isentropic efficiency is a relation between the ideal one or the isentropic one with the actual one. يعني if we see the equation for the isentropic or the isentropic efficiency, the deviation of actual pumps, compressor turbines from the isentropic ones can be accounted by utilizing isentropic efficiency. So isentropic efficiency for the compressor is the work is S, means يعني isentropic means S is constant, the entropy is constant. It is an isentropic, it is the ideal one when there is a compression process under isentropic يعني isentropic compression process. That is the ideal one. That is the process of the Carnot cycle. If you remember Carnot cycle contain isentropic compression process. Okay, يعني Carnot cycle, if you draw the TS diagram, it will look like a square like this, and it will be it will have a compression process from S1 مثلا to S2. Okay, so that is an isentropic process. Okay, we are comparing this one to the actual one. Why the actual in the denominator and the isentropic in the numerator? Because the numerator, the isentropic one will be less. Okay, always put the less in the numerator because you are losing work, you are consuming work. The compressor is a consuming device, consuming work, a work consuming device. Okay, work consuming device. Okay, and for turbine it will be the opposite. The actual will be in the in the numerator, because the work turbine is a work producing device. It is better for me to have a higher work, so it will be in the denominator. So this one will be always less than 1. Okay, and this one will equal to H2 minus H1. The difference is the same, the enthalpy at state 2 minus the enthalpy at state 1. Okay, but this one for the actual and this one for the isentropic. H1 is the beginning, okay, at the inlet of the compressor. So it doesn't matter with me, nothing happened. The process didn't happen yet, okay. So it is the same for both of them. So that's why it is in the green. But for the actual, it will be, it will not go in a straight line like this for the isentropic. It will be deviated, or not like the straight line. It will be like this or like this. I don't sure in which direction, but that is for the isentropic efficiency of the turbine. Okay, so we will use this equation. Okay, so I don't need this one now. For this one, the isentropic efficiency of the turbine, of the compressor, will be work.s. Now I have rate, so I put only dot. S mean isentropic, and over work.n actual, A or actual, whatever you want. Okay, and this one, we notice m dot h2 minus h1, or not this, both of them is m dot h2 minus h1. So, but the different is h2a minus h1, and this one is m dot h2s minus h1. Okay, that's why I wanted to put here in the energy balance h2a. Okay, and h1 I will not put anything. Okay, so this one is h2a. Okay, for C, the Exergy destroyed. C, Exergy destroyed. I will use T naught, the easiest way. T naught S dot generation. Okay, S dot generation is from S dot N minus S dot out plus S dot generation, the entropy balance. This will equal to 0 because there is no change in the system and the entropy rate. Okay, because it's steady process or steady device. Okay, so I have he said adiabatic, so there is no heat transfer. So I don't have Q over T. There is no entropy transfer by heat. So I only have entropy transfer by mass, and we said entropy transfer by work. There is no entropy transfer by work. It is always 0. Okay, so I have m dot s1 minus m dot s2 plus s dot generation, and this equal to 0. So s dot generation will equal to m dot s2 minus 1. This is small, kilojoule per kilogram. Okay, 1 will be the same, will not change. It is at the inlet. Okay, it doesn't matter it is isentropic or actual. But for S2, is it actual or isentropic؟ هي خلاص أنا شغال it is an actual cycle, so I am calculating for the actual cycle. Okay, that is why he did say it is part D for the second law efficiency. Okay, because he at the end he will see he will compare between the reversible and the actual, and it will be at the end in terms of X destroyed, and X destroyed it will be the actual one. Okay, we will see for the second law efficiency it will be the work reversible N over the work reversible actual N. Okay, and how to get the work reversible N? You need to subtract the exergy destroyed from the actual to get the reversible. Why I'm doing this? From where you get this equation? The other equation for the exergy destroyed, the other equation X destroyed is equal to what? Is equal to the work useful in or actual in, useful actual in, okay, minus the work reversible in, and equal to the irreversibility, okay. The work useful actual in, this one that I got from here, from the energy balance, okay. The work reversible in, I have to, I want to calculate it because I will calculate this in part A and I will calculate this in part C. So both of them are the actual one, okay. I will subtract both of them from each other, okay, so I can get the work reversible, okay. So this one is S2A. It is the actual one, okay. And he already didn't say anything about X destroyed. يعني يعني من الأساس يعني you cannot say there is X destroyed reversible one. يعني already in the Exergy balance we say it is equal to 0 when we make Exergy balance. To calculate usually the work reversible, we say when there is a reversible work, the Exergy destroyed is 0. So you cannot say this one is 2S because Exergy destroyed. It is not a reversible property. يعني. Okay, so this is S2A. Okay. What else? Okay, for part D is this one. We said, okay, it is work reversible in, and I will get it from this equation over the work useful actuals that I will get from part A, from the energy balance. Okay, what else I can use here for the okay, I need to find H2S, H2A. Okay, خلاص يعني that is it. يعني I don't need anything else. Okay. So let's get started. Part A was to find this one. So I need to find the mass flow rate, or it is given in the question. Oh, okay, I need to find it. So I have to get also V1 at state 1. So let's use the thermodynamics table, the refrigerant tables, to find everything that we want. Okay. So at state 1, I have T1 equal to negative 30 degrees Celsius, and X1 is equal to 1 because it is saturated vapor. He said saturated vapor. Okay, I will take everything at G. So V1 equal to VG, S1 equal to SG, and H1 equal to HG. Okay, this is a common state between the isentropic and the actual one. Okay. For the actual one, يعني B2, you will have state 2 actual and state 2 isentropic. Okay, so B2 is equal to 900 kilopascal or 0.9 megapascal, and T2 is 55 degrees Celsius. Okay, why I would say this one is actual? يعني why it is not the ideal one? Because let's draw the TS diagram and see what is the meaning of this. Draw this one. Okay, at the beginning, at state 1, I have a temperature, so this T and this S. I have temperature negative 30. Okay, and I am a saturated vapor, so I am here. That is my point. Okay, that is saturated vapor. Okay, I will go into ways. One is isentropic, so I will go exactly at a straight line. So a straight line. Okay, so it will be given the same value for S. So here I will get for this one is state 1, and we'll go up to state 2. So I can say it is isentropic compression, isentropic compression process. Okay, When you go up, it is isentropic compression. When you go down, it is isentropic expansion. If you want, you can search for the net on the BV diagram. BV diagram will show you how the volume or a specific volume will change. Okay, it will be the pressure will increase and the specific volume will decrease in the isentropic compression process. Okay. For the isentropic compression process, S1 equal to S2S. تمام. S2S. Okay. So I need to find S1 so I can get S2S, and from it I can get other properties. Okay. But if it is actual cycle, what is the other property at this temperature? يعني at this state 2. يعني for state 2 I know for the for state 2 B2 and T2. يعني B2 this one, B2 is 0.9 megapascal, and I know that T2 is 55 degrees Celsius. So I have two properties. I can get يعني easily the actual. This is the actual. But for the isentropic, when I have this one, I have the pressure 0.9 megapascal. Okay, that's the pressure B2. But if I use again the temperature, so what is the difference between the actual and the ideal isentropic cycle, isentropic process? What is the difference? So I have to use the property of the isentropic compression process, or the special thing about it. So it is the S1 equal to S2S. So I have to use S1 equal to S2S. تمام? S1 I will get it from the first equation here, so I can get S2S, and from S2S and the pressure I can get H2S, because I need it in the equation for the isentropic compression here, H2S. Okay. For the actual process I need H2A, and for the Exergy destroyed we said I need also S2A. Okay. So these 6 properties that I want to find. Okay, so let's start with the state 1. I have the temperature, and it is it's what? It is the refrigerant, right? Okay, it is refrigerant. So I have to go to table A11. Table A11. Okay, at temperature -30. Okay, and it is a saturated vapor, so I will get VG, HG, and SG. Okay, this will give you V1 0.2258 meter cubed per kilogram. S1 equal to S3 equal to 0.95579 kilojoule per kilogram Kelvin, and for H1 equal to Hg, this is 232.17 kilojoule per kilogram. Okay, that is for state 1. For state 2, I have the pressure and temperature. It is easier for me to go to the pressure. Okay, 900 kilopascal. Okay, this one. My temperature is 55. 55 is higher than 35.51, so it is a superheated state. So I would say T2 is higher than saturation temperature, 55 degrees Celsius is higher than 35.51 degrees Celsius, so it is superheated state. Okay. So H2A, I have to get it from the superheated table. Okay, superheated table, 900 kilopascal is 0.9 megapascal. Okay, 0.9 megapascal is here. At 55 degrees Celsius, it is exactly between 50 and 60. It is in the middle. Exactly in the middle, so I can only get the numbers for H and S. Yani this one 284.77 and 295.13, add them and divide by 2, as we did in the constant specific heat under constant pressure, CB. We'll do here also for entropy. We will add these two numbers, 0.966 and 0.9976, and divide by 2. We'll get our entropy and our enthalpy at 55 degrees Celsius. This you will do only if your temperature is exactly, or your property is exactly at the middle between other two properties. Else you have to do the regular interpolation. Okay. For H2A, it will be 295.13 plus 284.77 over 2, and this will give you 289.95 kilojoule per kilogram. And for S2A, let's write it here. S2A is equal to 0.966 plus 0.9976 over 2, and S2A will give you 0.9818 kilojoule per kilogram Kelvin. Okay. For state, for the isentropic state, okay, the ideal one, 0.9 megapascal, S1 equal to S2S. S1 is already what? S1 is 0.95579. Okay, and this one is equal to 0.95579 kilojoule per kilogram Kelvin. Okay, so what shall I do? I will go to table A12, the pressure table, and compare my entropy to the SG. So at 900 kilopascal, my entropy is 0.95, okay, 0.95579. So it is higher than SG. So when it is higher than SG, so it is superheated table. Okay, so you have to go to superheated table. So we will say that my entropy S2S, okay, is higher than SG, of course, at pressure 900 kilopascal. So 0.95579 is higher than 0.91692. So I have to go to the superheated table. So because it is a superheated state, superheated table. Okay, table A13 at 0.9 megapascal. 0.9 megapascal. My entropy is 0.95, so it is between these two entropies. So I have to make interpolation. Okay, interpolation with my entropy to find the enthalpy. I am doing all of this to find the enthalpy, the ideal or isentropic enthalpy at state 2. Okay, I have to make an interpolation between H and S. Okay, so I will make between these four with my entropy. Okay, 0.9327 the lowest, that is the highest, that is the corresponding enthalpy, that is the corresponding enthalpy to the highest one. Okay, so I will write them. The lowest one 0.9327. My enthalpy that I want to find H2S. Okay, wait. That's for entropy. This value is for entropy. Okay, so 0.9327, 0.95579, and 0.9660 is H2S 274.17, the corresponding enthalpy to the lowest entropy, and 284.77. So let's make the interpolation. 0.95579 my entropy minus the lowest one 0.9327 over the highest one 0.966 minus 0.9327 the lowest one equal to the enthalpy S2 H2S minus 274.17 over 284.77 minus 274.17. So H2S will equal to 281.52 kilojoule per kilogram. Okay, so I got every property that I want. So let's return back and find our requirements. So at part A, he wants to find the work in actual, okay, which is we said from the energy balance is m dot h2a minus h1, okay, and m dot is already v1 dot over v1, so times h2a minus h1, okay. So this will equal 7.5 times 10 to the power negative 3, that's the volume flow rate, over 0.2258, that is V1 that we got, times 289.95 H2A minus 232.17 will give me the work in dot in actual, the power is 1.92 kilowatt, okay. For part B, the isentropic efficiency is the work dot S, and don't mix between the isentropic work and the reversible work. They are not the same, okay? Over the work dot N actual, okay? Isentropic work means like Carnot cycle, isentropic compression, for the turbine, isentropic expansion, يعني the ideal one, okay? M dot H2S minus H1. This one is for the isentropic. Okay. M dot. Let's find M dot. يعني no need to write every time V dot over specific volume. So M dot is already 7.5 times 10 to the power negative 3, that's specific the volume flow rate over the specific volume 0.2258. This will give you m dot 0.0332 kilogram per second, okay. So 0.0332 times 281.52 minus 232.17 over 1.92, and this will give you 0.853, which is equal to 85.3%. Okay, for part C, we want to find the exergy destroyed, and we said it is equal to T naught S dot generation, and at the end the S dot generation from the Entropic balance is M dot S2, and we said it is actual minus S1. Okay, so T naught is 300 Kelvin, M dot it is 0.0322 or 32 times 0.9818 S2A minus 0.95579. So X destroyed will equal to 0.259 kilowatt, and all of these equations or all of this result يعني approximately the same like the solution manual, because the thermodynamics table they got very little different from our thermodynamics tables, so maybe they are using a new version or a new edition. So at the end, at part D, the result maybe will be different a little bit, but I don't think it is that different. Okay, not that much. Okay, this one is called the second law efficiency. Okay, the second law efficiency of the compressor. This is the work reversible N over work dot actual N, and you can find it here in the summary at the last page. Okay, for the compressor, it is the work reversible N over work N. Okay, So, but here we have power, so it is in dot and kilojoule per second, or you can say it is a work consuming device, so it is work reversible or work useful. Useful is the actual يعني. Okay. So this one can be written as يعني we know that x destroyed is equal to work dot actual n that we calculate from the energy balance minus work reversible n. So work reversible n can be written as w dot n actual minus x dot destroyed. So I'll write it here. So this one is w dot n actual minus x dot destroyed over work dot actual in actual. Okay. Distribute the denominator on the numerator. Okay, this will give you 1 minus x dot destroyed over work dot actual n. Okay, and this is 1 minus x destroyed, we got it already 0.259, this value. Okay, and actual n from the energy balance, it's 1.92. This will give you 0.865 equal to 86.5%. And if you want to find the work reversible n يعني as an additional requirement, work n actual is 1.92, x destroyed 0.259, and this will give you 1.661 kilowatts. And here the last question, we finished the last question. So thank you, and see you in the next video inshallah about nozzles and diffusers inshallah, Exergy nozzles and diffusers.